So let's go ahead then and start to model our lateral force FAY. So as in the previous chapter, we can write our lateral force at the trim condition as the product of a coefficient, the dynamic pressure, and the wing reference area, where our coefficient now is the lateral force coefficient, and that's a function of side slip angle, aileron deflection angle, and also the rudder deflection angle. So as always, we can apply a Taylor series expansion to get this, where now we have all of these coefficients of lateral force. So this first one here is the coefficient of lateral force when the side slip angle, the aileron deflection angle, and rudder deflection angle are all 0. And that's equal to 0 because if you think about it, if we have no side slip angle and the ailerons and rudder are all centralized, then we have no side force on the aircraft because of the symmetry of our aircraft, right? So then we have, up here we have coefficient of lateral force due to side slip, coefficient of lateral force due to aileron deflection angle, and coefficient of lateral force due to rudder deflection angle. Now the easiest one of these to deal with is this one, coefficient of lateral force due to aileron angle. We're going to assume that's approximately 0 because when we change the aileron deflection angle, the forces associated with doing that are drag, which is in the x direction, and also a change in lift, which is in the z direction. So in other words, there is no y component of force when we change the angle of the ailerons. So obviously they do induce a roll moment because they act in opposite directions, but the change in angle of the ailerons themselves do not exert a side force on the aircraft. The next easiest one to deal with is this one, the coefficient of lateral force due to rudder deflection. So let's have a look at that one. That can be given by this formula here. And by the way, our sign conventions tell us that positive rudder deflection angle, so trailing edge left, gives positive side force, so in the positive y direction, out the right wing, right? So positive rudder deflection gives positive side force. So we can calculate our coefficient of lateral force due to rudder deflection angle with this formula here, where we've introduced a couple of new terms. So first of all, tau r is called the control surface effectiveness factor for the rudder. We've seen a control surface effectiveness factor for the elevator previously, and this is found based on the ratio of the mean aerodynamic chord of the rudder and the mean aerodynamic chord of the vertical tail. And you can see how you calculate that in figure 4.261 in the textbook. The next term here, K sub r, is called the span factor, and that basically characterizes the relative size of the rudder versus the vertical tail. So again, how large is the moving bit compared to the whole size of the vertical tail, and that can be found based on the taper ratio of the vertical tail. So obviously the ratio of the tip to the root, and also the length of the rudder in comparison to the length of the whole vertical tail. And finally then, this term here, CL alpha V, the lift curve slope for the vertical tail, right? And that can be found again using the Polhemus formula, which we saw in the previous chapter. But now we have to consider the interference of the horizontal tail on the vertical tail, and you'll see how we do that in a moment. So that just leaves this term here to deal with, the coefficient of lateral force due to side slip, and we're going to have a look at that right now on page 2. Alright then, so this is our formula for the coefficient of lateral force due to side slip. So that's the formula that's the term that we just had over here, right? That's the only one that we're left to deal with. And you can see that we can break that up into coefficients of side force due to side slip on the wing and body, the horizontal tail and the vertical tail. So I'll explain my way around this flow chart, which obviously ended up a little bit more complicated than I intended, but when I upload this I'll color code it so you can see what terms are associated with which parts of my scrawlings. So let's deal with the easiest one first. So the coefficient of side slip due to side slip on the horizontal tail. So we're going to assume that is negligible because you can imagine that the effect of side slip on the horizontal tail is going to be much smaller compared to that on the wing, for example. But this effect does increase with dihedral angle. So exceptions to this rule include aircraft where the horizontal tail has significant dihedral angle. So for example, the McDonnell Douglas F4. Go and look at a picture of that aircraft if you're not familiar with it. So that's the first one dealt with. Now let's deal with the coefficient of side force due to side slip on the wing and body. And what we're going to do is split that up even further into two coefficients, one for the wing and one for the body separately. So again, as we just said with the horizontal tail, the coefficient of side force due to side slip on the wing is only significant if we have considerable dihedral angle, in which case we use this formula here where this term is the dihedral angle in radians. So let's have a look at the coefficient of side force due to side slip on the body. Well, let's consider this little diagram up here. So here's our free stream velocity hitting the right hand side of the aircraft, so that's a positive side slip angle. Here is our side slip angle affected by sidewash, but essentially a positive side slip angle makes a negative side force, right, in the negative y direction. Remember, positive y is at the right wing, so positive beta makes negative side force, and in that case you can see that is modeled by this formula here, and that's why we have the negative sign at the front. And this formula here is based on two new parameters which I'll explain right now. So the first one, k sub int, so that's, you can look up that and how to find it in figure 4.8 of the textbook, but basically it's based on two distances associated with our aircraft. First of all, this parameter z sub w, or z sub w, and that is the vertical distance between the fuselage centerline. So imagine this is a section of my fuselage and here's the wing. So the fuselage centerline is this one here. So that's the vertical distance between the centerline of the fuselage and the wing root chord at 25%. So here's my wing root, how it's attached to the fuselage, right? This is the chord, and then this is the distance between the centerline and the chord at 25% along it, assuming the front of the aircraft is this way, right? And also the fuselage height given by the parameter d. So that deals with k sub int. Now let's deal with this new funny term here, s sub p to v, or p arrow v. So s sub p arrow v, now bear with me on this one, it gets a bit fluid mechanics-y, but bear with it. So this term basically defines the x location at which the flow around the fuselage stops being a potential flow. So it stops being irrotational. And that occurs either when the boundary layer reaches a certain thickness, or we have this developing wake coming from various conflicting surfaces around the aircraft. So when either the boundary layer gets large enough or the weight gets significant is when the flow around the fuselage stops being potential. And we denote this point by capital X sub 0. And we can find this point where the flow stops becoming potential by considering basically the curvature of the fuselage. So at the back of the fuselage, when the curvature is maximum, so this is negative curvature, right? At the point where the negative curvature is maximum is this new point x1. So if we know a function defining the curvature of the fuselage, we can differentiate it to find the point of maximum negative curvature. Then to find x0, which is the point at which the flow is no longer potential, we just use this formula down here, where LB is the length of the whole fuselage. So once we know that, and we know this K sub int, we can put it into this formula and find the coefficient of side force due to side slip on the body. And that then goes into there. So we've dealt with that. Now let's finally deal with the coefficient of side force due to side slip on the vertical tail. So again, this is the free stream velocity affected by side wash onto the vertical tail. Positive beta makes negative side force due to side slip on the vertical tail in the same way as it did on the body. And we find this coefficient based on this formula up here, where again we have introduced some more terminology. So first of all, this lowercase k sub y beta v is found from figure 4.13 in the textbook, and again is based on some physical distances regarding the rear of the aircraft. Firstly, the height of the vertical tail itself, and secondly, the height of the fuselage at quarter chord of the vertical tail root. So this distance here. Then this term here, the eta sub v into 1 plus the change in side wash angle with beta, is found using this formula here, where we've introduced this term here, the sweep angle at a quarter chord of the vertical tail. So again, a quarter chord of the vertical tail, this is the sweep angle, so that goes into there. Again, we're using our z sub w term, which we defined over here, right? So then finally, we discussed this a little bit earlier on, but this lift curve slope for the vertical tail, it can be found using the Paul-Hamer's formula, but we need to consider the aerodynamic interference of the horizontal tail onto the vertical tail by converting our aspect ratio into what's called an effective aspect ratio using this formula, where again we've introduced even more terminology. C1 and C2 are aspect ratio factor coefficients, which characterize the interference of the fuselage and horizontal tail onto the vertical tail, and K sub HV, which is a coefficient which accounts for the relative size of the horizontal and vertical tail respectively. And you can look up the corresponding charts in the textbook. So once you've done all of that, you now put all of those values into the coefficient of lateral force due to side slip, and then finally we have all of the terms that fit within this equation over here.